Hi. In our last talk, we defined some new terms: local and absolute maximum and minimum values of functions. And we discussed that if x and y, if those were the two variables in your function, if they represented something in real life that you were really trying to find the most of or the least of, that absolute maxes and mins were going to be really important. And we'll get into that in a couple more talks, and we'll talk about that quite a bit. We also started to say that local maxes and mins will help us find out what a graph looks like. We can find out where the graph goes from increasing to decreasing or decreasing to increasing, and that's important on a graph. And we even define some how you would do that. So anyway, today our goal is to learn a little bit more about sketching graphs and what the derivative can do to help us find out what a graph would look like. So a little bit of review, I think, is in order. If you have a function y equals f of x, if we have some interval from a to b, then if the derivative f prime of x in that interval is positive, we know the derivative means the slope. So if the slope is positive, it makes sense that f of x is increasing. And vice versa, if f prime of x was negative, then f of x would be decreasing. So we have a way with the derivative to see if a function is increasing or decreasing. Then we proved that if f of x has a local maximum or minimum at some point x equals c, then one or two things has to be the case. That f prime of x equals 0 or f prime of c is undefined. So at that point x equals c, you either have to have a 0 derivative, like that, where it's a local max, or undefined. It's got to be one of those two cases. We knew it made sense that those were local max or mins, but we weren't sure that there wasn't some case we weren't thinking about. But now by proving it, we know that's the only place we ever have to go to look for local maxes and mins. Then, the absolute max and min, we found out, is either going to happen at a local maximum or minimum, so it could happen there, or it possibly, like if this was the entire domain from here to here, the absolute max would be the same as the local max. But if the domain continued and went like this, and that was the end of the domain, then that could be the absolute max. So the absolute max could happen at an endpoint of the domain. But at least now we know exactly where to look for absolute maximums. And again, we won't really talk about absolute maximums again until a couple more talks, but then we'll talk about it quite a bit. Okay, now, f of x has a local maximum at x equals c, and I'm reiterating, that's what we know. It has to either be at a 0 or undefined derivative, but the way you can really tell that it's a maximum is if the derivative goes from increasing to decreasing. I mean, if the derivative goes from positive to negative, if the function goes from increasing to decreasing. So we know by finding out where it's a 0 undefined derivative, the possible ones, but to prove whether it's a local max or a local minimum, we have to see where the derivative goes from positive to negative or from negative to positive. That would be a local minimum. So this would be going from positive to negative. And that would be the first derivative test to find local maximums. And the only thing you'd have to change if you wanted this to be the minimum would be f prime of x goes from negative to positive, and that would be the first derivative test for a local minimum. So that's kind of review of what we did. Now, a question you might have is, if we looked at number 2, it says if it has the max or min, it's going to be in one of these two cases. What if it doesn't go the other direction? What if the derivative is equal to 0 or undefined? Does that guarantee that it's either a local max or min? Well, we would have to prove that. But to disprove it, all we have to do is come up with one counterexample. And I think I can draw that for you. What if a function was decreasing like this and coming to a 0 derivative? Now, a 0 derivative could mean a local max or min. It might go like that, and then it would be a local minimum. But there's nothing to say that it can't decide, oh, I liked going down, and decide to go back down again. So in that case, you wouldn't call this point a local max or min. It's not the highest or lowest point in any neighborhood surrounding that point. So we have to know, yes, 2 is good to find possible local maxes or mins, but we really have to go to the first derivative test to find out which one of the two it is once we find it, because it might turn out to be neither. Okay, well, having said that, besides local maxes and mins, is there something else that would really be nice to know about the graph if we're trying to find out what it looks like so we can sketch it? What if I just took 2 points from here to here, and I was trying to sketch that graph? Well, there's different ways I could do it. I could do it in a straight line, or I could do it in this shape, or I could do it in this shape. Obviously, you could do a combination of those shapes, but just in general, there's 3 possibilities of the way to connect 2 points. So we should try to call these things something. Right here, this green shapes like this, and the red is this type of shape. So this has got a name. It's called concave up. And this is called concave down. And I don't know how you want to remember that. One way you can do this is say concave up like a cup, and concave down like a frown. Anyway, you can come up with your way you want to remember the name. But what we're really interested in is how can we tell, using the derivative, which way it's going to be? Well, you can see that the derivative here, since the function is decreasing, is negative, and the derivative here is positive because the function's increasing. So we can't say just by the sign of the derivative whether it's concave up or concave down. But what we can do is take a look at the derivatives. They go like from here to here to here. So what are those derivatives doing? They're going from a big negative to a medium negative to a wee little tiny negative to a zero slope. Then it goes to a wee little tiny positive to a medium positive to a big positive. So in that whole process, what's the derivative doing? It's going from big negative to less negative to positive to more positive. The derivative is always increasing. So we have a way with the derivative to find out whether it's concave up. We just to see where the derivative is increasing. Now, unfortunately, it's not always, if you're looking at a derivative formula, it's not always easy to find out whether it's increasing or decreasing. So, what did we do in the original case with a function if we wanted to know whether it was increasing or decreasing? We took its derivative. So we're going to do the same thing here. We're going to take the derivative of the derivative. And if it's positive, that means the derivative itself is increasing. So we can find out by looking at the second derivative. If the second derivative is positive, then the function is concave up. Yes, this is another clue right here, but it's just a little bit harder to use. Now, I'm not going to go through quite as much detail for concave down. I think you can see it's going to be just the opposite. You're going from a big positive slope to a medium positive slope to a wee little tiny positive slope to a zero slope, wee negative, medium negative, large negative. So altogether, what's the derivative doing? The derivative is decreasing in value. And if we take its derivative, the second derivative, we can just look to see where the second derivative is negative, and then the function is going to be concave down. And the third alternative, for a straight line, the derivative is always the same. It's neither increasing or decreasing. So if the derivative is constant, which means the second derivative is zero, then we have a straight line. So we've taken care of all the possibilities. Now, when we're going to sketch a graph, we're looking for special points on that graph. And we yesterday talked about the local maxes and mins as being special points, because the function itself is going from increasing to decreasing or vice versa. Well, since concavity seems to be an important part of the graph, maybe there's a new special point where it changes from one concavity to another. So if it's going concave down, and then all of a sudden it decides to go concave up, this point here is an important point on the graph. So we're going to give it a name, a point of inflection. It's sort of like when you're talking and you have a change in the pitch in your voice. They call that a change in inflection. So it's kind of a long thing, so if we write it a lot, sometimes I'll just call it a POI, point of inflection. Well, let's see if we can use what we've learned on some examples. Now, I could pick complicated examples, but I think if we start with simple functions that you already intuitively know what they look like, we can try some of our analysis and see if it comes out the way that you know that it should be. So take the function f of x equals x squared. I'm going to use what I know is the only way to find local maxes and mins is to take the derivative and see whether the derivative is equal to 0 or where it's undefined, because that's the only possible places. And it's 2x is never undefined, and it's equal to 0 when x equals 0. So if I put on my number line, on the whole real number line, the only possible point of a local max or min is at 0. But we still don't know for sure that it is a local max or min, so we have to use the first derivative test, which means we find out in this whole interval to the left of 0 whether it's positive or negative. Well, try any point in here. A negative number is going to make that negative. The positive number for x is going to make that positive. And we know it has to be that way this whole way, because the only way to change from positive to negative is if you go through 0 or some undefined jump. So we now know that 0, comma, and we can plug that into the original equation to get the y value. This is a local decrease, increase. Let's see what the function's doing. It's going down and then going up. It's a local minimum. And we could write no local maximums, because that was the only possible point where you could find a local min or max. So we found out one thing about that function. Everything you can find from the first derivative. Now let's go to the second derivative. What do we get? The derivative of 2x is 2. And to find possible points of inflection, we set that equal to 0 or undefined. Well, 2 is never going to equal 0, and it's never going to be undefined, so there's no possible points of inflection. What do we see? It's always concave up. So we know some things about this graph. We know that the only important point was 0, 0. We know the slope is 0 at that point. We know the function goes from decreasing to increasing, and it's always concave up. So I think that goes along with our intuition what y equals x squared would look like. Okay, let's go to a little bit more difficult one, but still one that we kind of recognize. F of x equals x cubed. The derivative is 3x squared. I set that equal to 0 or undefined. Again, the only point is x equal 0. We call that a critical point, right? And if I put it on the number line for the derivative, I see, oh, x squared. Everything is positive. So the function is always increasing. There's no place where it changes from increasing to decreasing or vice versa. Therefore, the first derivative test tells us there's no local max or min. Well, that's knowledge. Even though we didn't find something, that gives us knowledge of the graph. Well, let's go to the second derivative. See if that tells us anything. The second derivative is 6x. I'll set that equal to 0 or undefined. And again, the only point we find is for the second derivative, and I'm going to label it second derivative. It's never undefined, but at x equals 0, it's 0. And if I take something less than 0, 6x is going to be negative, and greater it's positive. So that means the function itself is going to be concave down where the second derivative is negative, and concave up where the second derivative is positive. So we find out that is a point of inflection. We knew it was the only possible point of inflection, and now we know that it really is. And 0 cubed is 0, so 0, 0 is the only important point. And we know we have a 0 slope there, and we know the function is always increasing, but it goes from concave down to concave up. So it's going to go increasing and concave down to a zero derivative, and then increasing but concave up. So that's what y equals x cubed looks like. And most of us, our intuition told us it was going to look like that. Okay, let's try f of x equals x to the fourth. The derivative is 4x cubed. Set that equal to 0 or undefined. Again, the only important point is x equals 0. That's the only critical value. Put that on the number line. F prime. It's the only critical value. If I take a number that's negative, x cubed is negative, then it goes to positive. So again, the function itself goes from, you can either write decreasing and increasing, or you can make the shape. Decreasing and increasing, you can see that that's a local minimum. You don't even have to memorize the first derivative test. You can just look to see what the graph looks like. So I now know that the only local max or min is at 0, 0 to the fourth. And it's a local minimum, and you could write no local max, just to show that you ruled that out. Now you can go to the second derivative, and you get 12x squared. And without even putting it on the number line, you can say that's always positive, or 0. So there can't possibly be any points of inflection because the concavity is always positive. So you can put it on the number line, but you don't even really have to. You can just say no points of inflection. And we've got all the special points. The only special point is 0, 0. The function goes decreasing to increasing, and the concavity is always positive, except this is looking just like x squared, except at x squared the concavity was 2. It was still concave up, but right here it flattens out. So it's a little hard to draw. It does look very much like y equals x squared, except right here there's no concavity. It flattens out for that instant, and it's fairly flat a little bit before it and a little bit after. Okay, let's just pick a little more complicated function and do one of those. So now we've got this cubic. And we have some idea what cubics look like. So let's take its derivative. 6x squared plus 6x minus 12. And if I factor that, we get 6 times x squared plus x minus 2, or 6 times x plus 2, x minus 1. So I've got it factored, and I want to see where that's equal to 0 or undefined. Well, it's never going to be undefined. It's a polynomial. That's defined everywhere. Where is it going to be 0? Well, when that factor is equal to 0, which is at -2, or when that factor equals 0 at 1. So if I put the derivative on the number line, I see 2 possible local maxes or mins. So now I'm just going to plug a number somewhere to the left of -2, a really large negative number you could pick if you wanted, but what are you going to see about the derivative? It's positive times negative times negative, so it's positive. An easy number to pick between -2 and 1 is 0. If you put 0 in here, you get positive times negative, and a bigger number than 1 is going to make all 3 of these factors positive. So the function is doing what? It's going increasing, decreasing, increasing. So we can see right here at -2, we have a local max, and at 1, we have a local minimum. Now, this is going to be a little bit more difficult to plug into the function. So I did it ahead of time and found that this was 20, and 1 gave you -7. So we found 2 important points on the graph. At -2, 20, and at 1, -7. These don't have to be perfect. Now let's go to the second derivative. The second derivative is 12x plus 6. And if I set that equal to 0 or undefined, to look for possible points of inflection, I find that the only possible point is when x equals -1/2. It's never undefined, and at -1/2, the second derivative equals 0. Again, that doesn't guarantee a point of inflection. We really have to see that the concavity changes. Well, if you take a number to the left of -1/2, this is going to be negative. So the function itself is going to be concave down. Bigger than 1/2, this expression is going to be positive. So the function is concave up. So sure enough, at -1/2, we have a point of inflection. And that happens, when you put -1/2 into here, it happens at 6.5. So at -1/2, 6.5, right there is I'll make it maybe different color. That's a point of inflection. So we've got all the important points on the graph. And what do we know? The function goes increasing until you get to -2. So the function's gone increasing, and then it decreases from -2 to 1, and then it increases for the rest of eternity. But I just sketched that lightly because now we want to sketch what it really looks like by putting in the concavity. It's concave down until you get to this point of inflection. So really, it's going to go concave down with a 0 slope here. We know that it's got a 0 slope there. And then it gets to this point, and it goes concave up. And we have a 0 slope here. So we have a pretty accurate representation of that graph. And I was awful lucky. Notice at 0, the function value is 0, so it should go through the origin there. I think I was just lucky there. But having the right shape is going to give us a better chance of having that much success. So we did it on 3 real easy graphs, one a little more complicated. The good thing is, this same process is going to be used on all functions to find local maxes and mins and points of inflection. So we don't have to, when we get new types of graphs, like trigonometric graphs, we don't have to learn something new. It's going to be done exactly the same way. Now, before I end this talk, there is the first derivative test to find local maxes and mins, and that's usually what you're going to use. But there is a second derivative test for local maxes and mins that sometimes is going to work a little bit better. So let's just see if it makes sense. What if you already found out that the first derivative at some point x equals c is 0? I've used up most of my board here, but what does that mean? You could have something like this where the derivative is 0. You could have something like this where the derivative is 0. Or you could have something like this where the derivative is 0. But in this case, you all have different concavities. This one is concave down. So the second derivative is negative. This is concave up, so the second derivative is positive, and this is a point of inflection where the second derivative equals 0. So I can say, just looking at the shape, if the second derivative is greater than 0 and the first derivative equals 0, it must be this case here. You have a local minimum. So f of x has a local minimum. And if the first derivative is 0 and the second derivative is negative, then we have a local maximum. Now, you might say, if the second derivative is 0, we have a point of inflection, because it looks like it right here. But, what did we find over here? We found the second derivative was 0, and the first derivative was 0. On y equals x to the fourth, both the first derivative is 0 and the second derivative is 0, and it turned out to be a local minimum. So the test fails. It could be a point of inflection, like it was on x cubed, and it could be a local minimum or maximum. So the test fails. You just have to go back to the first derivative test. And it would have worked here. We would have tried the second derivative test and found out that it was equal to 0. On this one, we still could have gone back and found out that it was a local minimum using the first derivative test. So I wouldn't worry as much about this one, but I hope you understand the concept there. Anyway, that pretty much takes care of how you would go about sketching a graph using the derivative. And a little practice will make so we can get some pretty good sketches of graphs. So, have a good rest of your day.